All right, let's dive into one of the biggest showdowns in the history of science. This was a battle that lasted for centuries, with some of the smartest people who ever lived going head to head. And it was all about one simple yet incredibly deep question. What is light, really?
Yeah, that was the big one. Is light a bunch of tiny little particles, like a spray of bullets? Or is it more like a wave, a ripple spreading out in a pond? It might sound simple, but let me tell you, the answer to this question was going to change everything we thought we knew about the universe. Okay, so let's meet our contenders. In this corner, representing Team Particle, you've got the absolute heavyweight champion of physics, Sir Isaac Newton. And in the other corner, fighting for Team Wave, is the brilliant Dutch physicist Christian Huygens. You've got two titans of science living around the same time, with two completely different ideas. So, Newton's theory was called the corpuscular theory. A fancy word, but the idea was pretty simple. He thought light was made of tiny little particles, or corpuscles. And you know what? It made a lot of sense. Light travels in straight lines, right? It bounces off a mirror just like a ball bounces off a wall. His model, which he wrote about in his super famous book, Optics, just seemed to work for everything people could see back then. But then you have Huygens, and he comes along with this much weirder idea. He's saying, no, it's not like a bullet at all. It's more like a wave spreading out in all directions, like when you drop a rock in a lake. For his time, this was a totally out there, radical concept.
Now, to really get what Huygens was on about, you gotta understand this key concept called a wavefront. It's actually pretty easy to picture. Just imagine that ripple in the pond again. The wavefront is just that expanding circle, that leading edge of the ripple where all the water is rising up at the same instant.
And this is where Huygens was just brilliant. He came up with a way to predict where the wave would go next. He said, okay, imagine every single point on that wavefront is creating its own tiny new little ripple, a wavelet. And the next wavefront is just the line you can draw that touches the front edge of all those new little wavelets. It's an incredible geometric trick, and it let him map out exactly how a wave would move and even bend around things.
Okay, so here's where it gets really interesting. This is the moment the two theories have a direct, head-to-head showdown. They made a prediction about what happens when light goes from air into something denser, like water, and their predictions were the exact opposite. Newton's particle theory said light should speed up. Huygens' wave theory said it had to slow down. I mean, they couldn't both be right. One of them had to be wrong.
The problem was, nobody could actually measure the speed of light in water back then. The technology just wasn't there. It took, get this, over 150 years. Finally, in 1850, a French physicist named Foucault pulled it off. And the verdict? Light slows down in water. Bam! A huge, undeniable win for Team Wave. But you know what's crazy? Even before Foucault's measurement, another piece of evidence had shown up. I'm talking about a real smoking gun. An experiment so simple, so elegant, but so powerful that for a lot of physicists, it had already ended the debate. This was back in 1801, and the man behind it was Thomas Young.
Young's experiment started with a really simple question. What happens if you shine light through two super tiny parallel slits? What kind of pattern would show up on a screen behind them? It turns out this simple setup was the ultimate test, because the particle and wave theories predicted completely different things. Think about it. If light is made of particles, like tiny paintballs, you'd shoot them through the two slits and you'd just get two bright lines on the wall behind, right? One line for each slit. Makes sense. But that is not what Young saw. Not even close. What he got was this crazy, beautiful pattern of multiple bright and dark bands. It made zero sense for particles. But for waves, it's exactly what you'd expect. So what's going on here? It's a phenomenon called interference. The waves coming from the two slits spread out and start to overlap. Now, where the crest of one wave meets the crest of another, they add up and you get a bright spot. But where the crest of one wave meets the trough of another, they completely cancel each other out, and you get nothing, darkness. Think about that for a second. You can add light to light and get total darkness. Mind-blowing. After Young's experiment, it was like the floodgates just burst open. Once scientists started thinking of light as a wave, they suddenly started seeing all these other behaviors that the particle model just had no answer for. A big one is something called diffraction. This is just the natural tendency of any wave to bend a little bit when it passes the edge of an object.
It's the reason you can hear someone talking from around a corner, right? The sound waves bend around the corner. Well, it turns out light does the exact same thing, just not as much. And that's actually why shadows are never perfectly razor sharp. There's always a little bit of fuzziness at the edge. You know, people sometimes get interference and diffraction confused, and for good reason. They're really just two sides of the same coin. The legendary physicist Richard Feynman pointed out that there's no real fundamental difference. He said it's just a question of usage. Basically, we call it interference when we're talking about a few wave sources, like in the double slit experiment. We call it diffraction when we're talking about countless wave sources, like all the points along the edge of an obstacle. So the case for the wave theory is looking pretty solid, right? But there was one final nail in the coffin for the particle theory. One last piece of evidence that didn't just prove light was a wave, but it told us exactly what kind of wave it is. And that property is called polarization. Polarization proves that light is what's called a transverse wave. The easiest way to picture this is to think about shaking a rope. You can shake it up and down, or you can shake it left and right. See how the wave travels forward, but the rope itself is moving perpendicular to that direction? That's a transverse wave. Light does this too, and this ability to be polarized is something that only transverse waves have. Okay, so by the mid-1800s, the wave theory was king. It seemed unstoppable. But there was this one giant, nagging problem. Think about it. Ocean waves travel in water. Sound waves travel in air. Every wave they knew about needed something to travel through, a medium. So what was light's medium? How does light from the sun get to us through the total empty vacuum of space? The answer, incredibly, didn't come from someone studying light. It came from a physicist who was working on something that seemed totally separate: electricity and magnetism. This was the genius James Clerk Maxwell. And what he did was unify all the known laws of electricity and magnetism into one beautiful, elegant set of equations. And buried inside those equations was a bombshell. They predicted the existence of a wave made of electric and magnetic fields that could travel all on its own, no medium required. And here's the kicker. When Maxwell calculated how fast this electromagnetic wave should travel, the number he got was a perfect match for the measured speed of light. The conclusion was just inescapable. Light isn't traveling in something. Light is the thing that's traveling. It's a wave of pure electromagnetism. So let's just quickly recap the three big knockout punches that proved light is a wave. First, you've got interference. That's the double slit experiment. Second, diffraction, the way light bends around corners. And third, polarization, the proof that it's a transverse wave. The bottom line is, these three things simply cannot happen if light is a particle. They are defining behaviors of a wave. Which brings us back to that final, incredible question: if light is a wave, what exactly is waving? And the answer is just, well, it's beautiful. It's not water, it's not air, it's the fundamental forces of the universe itself. An electric field and a magnetic field, constantly creating each other, oscillating back and forth as they fly through space. It's a self-sustaining ripple in the very fabric of reality. What an amazing answer to one of the longest debates in science.